It was late 1997 and early 1998. The universe, we thought, was a simple story. It began with a bang, it was full of matter, and that matter's gravity was pulling everything back together. The expansion, started by the Big Bang, had to be slowing down. The only question was by how much? Was there enough stuff to eventually halt the expansion and cause a big crunch? Or would it just slow down forever, coasting into a cold, dark future? Two teams of astronomers set out to measure this deceleration. One was the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other was the High-Z Supernova Search Team, co-led by Brian Schmidt and Adam Riess. They used the same brilliant technique. They would look for a specific type of exploding star, a Type Ia supernova. These supernovas are special. They happen when a white dwarf star, the dead remnant of a sun-like star, sucks material off a companion star. When the white dwarf hits a precise mass, about 1.44 times our sun, it ignites in a thermonuclear explosion of unimaginable power. Because they all explode at the same mass, they all have roughly the same intrinsic brightness. They are cosmic standard candles. If you see one that looks dim, it's far away. If it looks bright, it's closer. By measuring their redshift, which tells you how much the universe has stretched since the light left the star, you can map the expansion history of the universe. The work was a slog. They had to find these faint, fleeting explosions in distant galaxies. They had to measure their brightness with incredible precision. They had to account for dust. By early 1998, both teams had their data, and the data made no sense. The distant supernovas, the ones that exploded billions of years ago, were dimmer than they should have been. They were farther away than any model predicted. This wasn't a small error. It was a consistent, stubborn fact in the data. The only way for them to be that far away was if the expansion of the universe hadn't been slowing down at all. In the time since those stars exploded, the expansion had actually sped up. The universe was accelerating. The two teams checked and rechecked their work. They looked for every possible error. They couldn't find one. Reluctantly, they came to the same conclusion. Some strange, repulsive force was at work in the cosmos. It was pushing space itself apart, overwhelming gravity on the largest scales. They didn't know what it was. They just knew it was there. They gave it a name, a placeholder for their profound confusion, dark energy. That discovery, announced in 1998, didn't just answer a question. It broke our entire picture of the cosmos and left us with a set of questions so deep, so fundamental, that they still keep physicists up at night. Number 16, we call it dark energy, but we don't know what it is. The substance we call dark energy makes up an estimated 68.3% of the total energy density of the universe. Normal matter, the stuff that makes up stars, planets, and us, is only 4.9%. The name dark energy was coined by cosmologist Michael Turner in 1998, and it was intentionally chosen to sound mysterious and parallel dark matter. Its existence is not directly observed. It is inferred from the accelerating expansion of space-time itself. The first thing to get straight is that the name is a bit of a misnomer. It's dark not because it's black or shadowy, but because it doesn't interact with light. It doesn't emit, reflect, or absorb light or any other form of electromagnetic radiation. It is, for all intents and purposes, invisible. We can't point a telescope at a patch of sky and see dark energy. We see its effect. We see galaxies rushing away from us faster than they should. That's it. That's the entire observational footprint of the most dominant thing in the cosmos. It's also not energy in the way we normally think of it. It's not a cosmic battery or a fuel source. A better term might be negative pressure. Think of a gas in a balloon. The pressure of the gas pushes outward on the fabric of the balloon, making it expand. But the gravity of the gas particles also pulls them together. Dark energy is different. It has a powerful, persistent negative pressure. This is a concept from Einstein's general relativity. It means the substance doesn't just push outward, it acts as a source of anti-gravity. It creates a repulsive force that is a property of space itself. This is what makes it so different from dark matter, the other dark component of the universe. Dark matter makes up about 26.8% of the cosmos. It's also invisible, but it behaves like normal matter in one crucial way: it has gravity. Dark matter clumps together. It forms vast halos around galaxies, and its gravitational pull is what keeps those galaxies from flying apart. We can map the presence of dark matter by looking at how its gravity bends the light from distant objects, a phenomenon called gravitational lensing. Dark matter pulls things together. Dark energy pushes them apart. So what do we actually know? We know its density. It's incredibly low. The estimated energy density of dark energy is about 10 raised to the power of 29 grams per cubic centimeter. That is an absurdly small number. It's roughly the energy equivalent of a few hydrogen atoms in a volume the size of a large room. But because it exists everywhere, even in the vast emptiness of intergalactic space, it adds up. The sheer volume of the universe makes this tiny, tiny density the dominant force overall. While gravity wins inside a galaxy, dark energy wins in the voids between them. The current leading model for the universe is called the lambda CDM model. The CDM stands for cold dark matter. The lambda, the Greek letter L, is the symbol for the cosmological constant, which is our simplest and best guess explanation for dark energy. In this model, dark energy is a constant, uniform field that fills all of space. As the universe expands, new space is created, and this new space comes with its own fixed amount of dark energy. The density of dark energy never changes. It doesn't get diluted as space expands, unlike matter. This is why it eventually came to dominate the universe. As the universe grew, the density of matter and dark matter thinned out, but the density of dark energy remained constant. A few billion years ago, it reached the tipping point where its repulsive force overtook matter's gravitational pull on a cosmic scale. But calling it lambda is just putting a more technical sounding label on our ignorance. It's a parameter we plug into our equations because it makes them match the data. It describes the what that the expansion is accelerating. It doesn't explain the why. What is the physical source of this constant energy? Is it a fundamental property of the vacuum of space? Is it a new type of energy field we haven't discovered yet? Is it something else entirely? Well, we don't have a clue. It's the biggest line item in the cosmic budget, and it's currently written in as miscellaneous. Number 15, is it just a constant number baked into reality? Albert Einstein inserted the cosmological constant into his equations for general relativity in 1917. He did this because his theory predicted a dynamic universe, one that should be either expanding or contracting, but the prevailing view at the time was of a static, unchanging cosmos. The cosmological constant lambda acted as a repulsive force to perfectly balance gravity and keep the universe still. When Edwin Hubble discovered in 1929 that the universe was in fact expanding, Einstein famously called lambda his biggest blunder and discarded it. Yet, the 1998 discovery of cosmic acceleration brought it back from the dead. It might be his most prescient idea. The simplest explanation for dark energy is that it is the cosmological constant. This isn't just a random guess, it's a possibility that falls right out of Einstein's original theory of general relativity. In this framework, dark energy isn't a thing in space. It is a property of space. It is the intrinsic energy of the vacuum itself. Empty space is not truly empty. It has a fundamental rock-bottom energy level, and according to general relativity, any form of energy affects the curvature of space-time. The energy of the vacuum, it turns out, would have this strange property of negative pressure, causing a cosmic repulsion. If dark energy is the cosmological constant, then its density is, well, constant. It is the same everywhere in space and at all times in history. Its value today is the same as it was a billion years ago, and it will be the same a trillion years from now. It doesn't change, it doesn't dilute. It's a fundamental constant of nature, like the speed of light or the gravitational constant g. This has profound implications for the future. As space expands, the density of matter and dark matter drops, but the density of a cosmological constant stays the same. This means dark energy becomes more and more dominant over time. The acceleration we see today is just the beginning. The expansion will become exponential. Galaxies will be pushed away from us at ever-increasing speeds. Eventually, they will cross a cosmic horizon, their light no longer able to reach us, no matter how long we wait. The sky will empty out, leaving our own local group of galaxies as a lonely island in an endless expanding void. This fate is known as the Big Freeze or heat death. It's a cold, desolate, but predictable end. This idea fits the current observational data very well. Our best measurements from the Planck satellite, which observed the cosmic microwave background, and from surveys of large-scale structure in the universe, are consistent with dark energy being a cosmological constant. Our scientists use a parameter called OO to describe the equation of state of dark energy. This parameter is the ratio of its pressure to its energy density. For a true cosmological constant, W must equal 1 exactly. Our current measurements pin W to be very close to 1, somewhere in the range of 1.03 plus 0.03. But consistent with is not the same as proof. The measurements have error bars. It's possible that W is not exactly 1. It could be 0.99 or 1.01. This tiny deviation would mean that dark energy is not a constant, but something else, something dynamic. And that would change everything. The cosmological constant idea is simple and it fits the data. That's why it's the centerpiece of our standard model of cosmology, but it comes with its own colossal baggage. The biggest problem is its value. When physicists use quantum field theory to try and calculate what the energy of the vacuum should be, the number they get is gigantic. It is 10 raised to the power of 120 times larger than the value we observe. This is the single worst theoretical prediction in the history of physics. It's a discrepancy of 120 orders of magnitude. Why is the observed value so exquisitely small compared to the theoretical one? No one knows. It's as if two fundamental theories of nature, general relativity and quantum mechanics, are screaming at each other. Something is deeply wrong with our understanding. So, while the cosmological constant is the simplest explanation, it is by no means a satisfying one. It papers over a chasm in our knowledge. Number 14. What if we got the math wrong and gravity is different? General relativity, Einstein's theory of gravity, published in 1915, has been stunningly successful. It perfectly predicts the orbit of Mercury, the bending of starlight by the sun, and the existence of gravitational waves detected by LIGO starting in 2015. Every test we've thrown at it in the solar system, it has passed with flawless precision. But the acceleration of the universe is a phenomenon on a cosmic scale far larger than our solar system. Could it be that, on these immense scales, gravity itself behaves differently? This is the central idea behind a class of theories known as modified gravity. Instead of inventing a new, mysterious substance like dark energy to explain the cosmic acceleration, these theories propose that we don't need it. The acceleration is a natural consequence of gravity behaving in a way that Einstein didn't foresee. We are not seeing the effect of a repulsive energy. We are seeing a weakening of gravity's pull over vast distances. It's an appealing idea. It would solve the problem of dark energy by simply declaring it doesn't exist. It's an illusion created by using the wrong gravitational formula, but modifying general relativity is incredibly difficult. You can't just tweak the equations without breaking all the things that work so well. Any new theory must reduce to standard general relativity in high-density environments like our solar system, while producing cosmic acceleration in the low-density voids of space. This is a very fine needle to thread. There are many different approaches to modifying gravity. One of the simplest is called FR gravity, where R is a term in Einstein's equations called the Ricci scalar. In this model, you add a new function of R to the equations. By choosing this function carefully, you can make gravity behave differently on different scales. Another idea involves extra dimensions. In the Dvali-Gabadadze-Parati DGP model, our four-dimensional universe 3 space, one time is a brain floating in a higher dimensional space called the bulk. Gravity can leak off the brain into the bulk over very large distances. This leaking would make gravity appear weaker than expected on cosmic scales, leading to an apparent acceleration. The key to testing these ideas is to look for subtle differences in how the universe evolves. While a cosmological constant dark energy would cause space to expand uniformly, some modified gravity theories predict that the growth of structures like galaxy clusters would be different. They would grow at a slower rate than in a universe with standard gravity and dark energy. So, astronomers are meticulously mapping the distribution of galaxies and the growth of clusters over cosmic time. By comparing these maps to the predictions of different theories, they can search for telltale signs of modified gravity. Another powerful test involves gravitational lensing. As light from a distant galaxy travels towards us, its path is bent by the gravity of the matter it passes. Modified gravity theories can predict a different amount of lensing than general relativity, even if both theories produce the same overall expansion rate. The Euclid Space Telescope, launched in 2023, and the Nancy Grace Roman Space Telescope, planned for later this decade, are designed to make extremely precise measurements of gravitational lensing on a cosmic scale. Their data will be a crucial test for these theories. So far, general relativity is holding up. There is no convincing evidence for a modification of gravity on cosmic scales. The data we have from things like the cosmic microwave background and galaxy clustering are all beautifully consistent with the standard lambda CDM model. But the possibility remains. It's a battle between two strange ideas. Is there an invisible energy filling all of space, or is the fundamental force that holds the cosmos together not what we think it is? The answer lies in making our observations just a little bit more precise, to see if the cracks in Einstein's theory finally start to show. Number 13 is dark energy, actually a new kind of field. Perhaps dark energy is not a constant property of space, and it's not a misunderstanding of gravity. Perhaps it is a new dynamic entity, a type of energy field that fills the universe. This idea is broadly known as quintessence. The name comes from the classical fifth element proposed by the ancient Greeks to be the pure substance that made up the heavens. Unlike the cosmological constant, a quintessence field would not be static. It could change over time and vary from place to place. A quintessence field would be something like an electric or magnetic field, but with very different properties. It would have a value at every point in space, and this value could evolve according to some physical law. This evolution would determine its energy density and its pressure. The key feature would be that its potential energy would cause the negative pressure needed for cosmic acceleration. This solves one of the major conceptual problems with the cosmological constant. If dark energy is a dynamic field, its value doesn't have to be a fixed fundamental constant of nature. It could have started with a very different value in the early universe and evolved to the small value we see today. This might offer a way out of the fine-tuning problem, where the cosmological constant's value seems absurdly and precisely tuned. Instead of a fixed number, it's a process. The behavior of a quintessence field is often described using the analogy of a ball rolling down a hill. The position of the ball represents the value of the field, and the shape of the hill represents its potential energy. If the hill is very flat, the ball rolls very slowly. In this slow roll scenario, the field's kinetic energy is tiny compared to its potential energy. This condition is what generates the negative pressure that drives acceleration. The universe accelerates as long as the ball is slowly rolling down the hill. This dynamic nature opens up a whole new range of possibilities for the future of the universe. If the potential hill gets steeper, the field can speed up, causing the acceleration to slow down or even stop. If the potential has a minimum, the field could eventually settle there and dark energy would disappear. Even more exotic possibilities exist. One is called phantom energy. In this scenario, the quintessence field rolls uphill instead of down. This is physically very strange and would require some new exotic physics, but it's a mathematical possibility. A phantom energy field would have an equation of state parameter W less than 1. This would mean its energy density actually increases as the universe expands. The cosmic acceleration would become faster and faster over time. This leads to a spectacular and terrifying end for the universe known as the Big Rip. In this scenario, the repulsive force of phantom energy would eventually become so strong that it would overcome all other forces. In the final moments, it would tear apart galaxy clusters, then galaxies, then solar systems, then planets, and finally, it would rip apart individual atoms and the fabric of space-time itself. Current observations put tight constraints on these models. As mentioned, the measured value of W is very close to 1. This favors the cosmological constant. However, the measurements still allow for a small amount of evolution. It's possible that W is not 1, but 0.98. And has been slowly changing over billions of years. Our current instruments are not yet sensitive enough to definitively rule this out. So the search is on for any sign of dynamism. Projects like the Dark Energy Survey, DES, and the upcoming Legacy Survey of Space and Time LEST at the Vera C. Rubin Observatory are designed to track the expansion history of the universe with unprecedented precision. By measuring thousands of supernovae and mapping the distribution of millions of galaxies, they will be able to see if the acceleration rate has been constant or if it has changed over time. Any detection of a change would be a bombshell. It would rule out the cosmological constant and prove that dark energy is a new dynamic force of nature, a true quintessence. Number 12. What if the universe isn't as smooth as we think? Our standard model of cosmology is built on a foundational assumption called the cosmological principle. This principle states that, when viewed on a large enough scale, the universe is homogeneous and isotropic. That means it looks roughly the same everywhere and in every direction. There isn't a special center or an edge. This assumption has been a cornerstone of cosmology for a century and is strongly supported by observations of the cosmic microwave background, which is incredibly smooth. But what if this assumption is subtly wrong? The universe is obviously not smooth on small scales. It's clumpy, it has galaxies, stars, and planets with vast empty voids in between. The standard approach is to average over these structures, assuming they don't significantly affect the overall expansion. But some physicists question this. They argue that the complex, lumpy structure of the universe could, in itself, create the illusion of cosmic acceleration. This idea is known as backreaction. The argument is that Einstein's equations are notoriously complex and non-linear. Solving them for a perfectly smooth, homogeneous universe is relatively straightforward. But solving them for a realistic, lumpy universe is practically impossible. The standard method is to first average the distribution of matter and then solve the equations for that averaged, smooth universe. The backreaction hypothesis suggests this is the wrong way to do it. The non-linear nature of gravity means that the average of the solutions is not the same as the solution for the average. In this view, the intricate interplay of gravity within the cosmic web of clusters, filaments, and voids could produce large-scale effects that mimic a cosmological constant. The expansion rate inside a dense region like a galaxy cluster would be different from the expansion rate in a giant void. Perhaps the combined effect of all these local variations in expansion when we observe them from our particular vantage point within the structure conspires to look like a smooth overall acceleration. A related idea suggests that we might be living in a particularly empty part of the universe, a giant cosmic void. If we were near the center of a vast underdense region, galaxies outside the void would naturally be pulling away from us faster than those inside. From our perspective, it would look like an accelerating expansion, driven by the pull of the denser regions of the universe beyond our void. It would be a local effect, not a global property of the universe. These are intriguing but controversial ideas. Most cosmologists believe that the effects of back reaction are too small to account for the observed acceleration. Numerous studies have tried to model these effects, and the consensus is that they can't explain the data from supernovae and the cosmic microwave background. The giant void hypothesis is also constrained by observations. If we lived in such a void, we would expect to see specific signatures in the cosmic microwave background, and those signatures haven't been found. However, these ideas highlight a crucial point. Our conclusion that dark energy exists is based on interpreting observations through the lens of a specific model, the smooth Friedmann-Lemaitre-Robertson-Walker-Fleurieu model. If the foundational assumptions of that model are even slightly off, our conclusions could be skewed. The challenge is to develop mathematical tools and computer simulations powerful enough to accurately model a lumpy universe governed by the full, non-linear equations of general relativity. This is an area of active research. While it's considered a long shot by many, the possibility remains that dark energy is not a new substance or a new law of physics, but a phantom born from the complexity of the cosmos and our own simplifying assumptions. It's a humbling reminder that our grand cosmic conclusions depend entirely on the models we use to make sense of the light reaching our telescopes. Number 11, why did it only show up now? Of all the strange things about dark energy, this might be the strangest. For most of the universe's 13.8 billion year history, dark energy was insignificant. In the early universe, the cosmos was dense and hot and dominated by radiation. As the universe expanded and cooled, matter took over. For billions of years, the universe was matter-dominated. The gravity of matter and dark matter was in charge, slowing down the cosmic expansion. Then, only about 5 or 6 billion years ago, something changed. The universe had expanded enough that the density of matter had dropped to a critical point. At that point, the constant, unchanging density of dark energy finally became greater than the density of matter. The cosmic tug-of-war was won by the repulsive force of dark energy, and the universe's expansion began to accelerate. This leads to the coincidence problem. Why is this happening now? Why do we happen to be living in the very specific and possibly very brief cosmic era when the energy density of matter and the energy density of dark energy are of the same order of magnitude? Their values are within a factor of 2 or 3 of each other. This seems like an incredible coincidence. Think about the history of the universe. For the first 9 billion years, the density of matter was orders of magnitude greater than the density of dark energy. In the far future, the density of dark energy will be orders of magnitude greater than the thinning density of matter. The two values are only comparable for a relatively short sliver of cosmic time, and that sliver is the one in which we evolved and built telescopes to observe the cosmos. If dark energy is a true cosmological constant, this coincidence is particularly baffling. The density of matter falls as the cube of the scale factor of the universe as the volume increases. The density of the cosmological constant does not change at all. The two quantities evolve in completely different ways. For them to be so close today seems to require that their initial values at the time of the Big Bang were set with an absurd level of precision. It's a form of cosmic fine-tuning. This problem has led some physicists to consider more exotic models. Perhaps there is a connection between dark energy and dark matter. In coupled quintessence models, the two dark components don't just ignore each other. They interact. There could be a slow transfer of energy from dark matter to dark energy, or vice versa. This interaction could regulate the evolution of their energy densities, making it more natural for them to be comparable today. However, there is currently no evidence for such an interaction, and these models are difficult to test. Another more philosophical explanation is the anthropic principle. This principle suggests that we shouldn't be surprised to find ourselves living in a universe that has the properties necessary for life to exist. If dark energy had been much stronger, the universe would have started accelerating much earlier. And gravity would not have had time to pull matter together to form galaxies, stars, and planets. The universe would have been a thin, cold, empty place with no structures and no life. If dark energy were much weaker or non-existent, the universe might have recollapsed in a big crunch long ago. So the argument goes, we find ourselves in this specific era because it's the only kind of era that could produce observers. The densities of matter and dark energy have to be comparable for galaxy formation to proceed long enough to allow for the evolution of intelligent life. This is not a satisfying explanation for many physicists. It feels like giving up on finding a physical reason. It explains the why by saying, it had to be this way for us to be here to ask the question. But in the absence of a compelling physical theory, it remains a possibility that many are forced to consider. The coincidence problem highlights that the mystery of dark energy isn't just about what it is, but when it is. Number 10. Does dark energy interact with anything else? Our standard model of cosmology, lambda CDM, makes a very simple assumption. Dark energy and dark matter exist in their own separate worlds. Dark matter interacts with other matter, and itself only through gravity. Dark energy, as the cosmological constant, is just a property of space-time and doesn't interact with anything at all. They are the universe's two great introverts coexisting in the same space but completely ignoring each other. But what if this simple picture is wrong? What if the two dominant, mysterious components of our universe are secretly talking to each other? This is the idea behind a class of models known as interacting dark energy or coupled quintessence. In these models, dark energy and dark matter are not independent. There is a flow of energy between them. The idea is compelling because it could potentially solve some of the puzzles of dark energy, particularly the coincidence problem. If dark matter can decay into dark energy or vice versa, it could create a feedback loop that synchronizes their densities. Imagine a scenario where the rate of energy transfer depends on the relative densities of the two components. This could naturally lead to a situation where their energy densities remain comparable for a long period of time, rather than just by chance at the present moment. Or it would make the current state of the universe seem less like a wild coincidence and more like a stable or semi-stable equilibrium. How would such an interaction work? We don't know the specifics because we don't know what either dark matter or dark energy actually is. But theorists can write down the mathematical forms such an interaction could take. It could be a continuous slow drain of energy from the dark matter sector into the dark energy field. This would mean that dark matter particles are not completely stable, but have an incredibly long lifetime, slowly decaying over billions of years into whatever constitutes dark energy. Or the energy could flow the other way. Detecting such an interaction is extremely challenging. We can't observe either component directly, so we have to look for the subtle secondary effects of their interaction on things we can see. If dark matter is decaying into dark energy, it would affect the rate at which dark matter halos around galaxies grow. The growth of cosmic structures would be slightly suppressed compared to the predictions of the standard model. If the interaction goes the other way, the growth might be slightly enhanced. Astronomers are looking for these signatures. By using gravitational lensing to map the distribution of dark matter at different cosmic epochs, and by studying the clustering of galaxies on large scales, they can measure the history of structure growth. The Euclid and Roman space telescopes will be powerful tools for this. They will create vast 3D maps of the dark matter distribution, allowing for a very precise test of its evolution. Any deviation from the standard lambda CDM prediction could be a sign that The dark sector is more complex and interactive than we thought. There are also potential hints in the cosmic microwave background CMB. An interaction between dark energy and dark matter in the early universe could leave a faint imprint on the temperature fluctuations of the CMB. The data from the Planck satellite is so precise that it can be used to constrain these interaction models. So far, the data is consistent with no interaction, but the error bars still leave room for a small coupling. If an interaction were ever discovered, it would be a revolution in cosmology. It would mean the dark 95% of the universe is not just two separate mysteries, but a single interconnected dark sector with its own complex internal physics. It would provide a crucial clue to the fundamental nature of both dark matter and dark energy, and it might just solve the nagging coincidence problem that haunts our current understanding. Number 9. What was it doing in the early universe? In our standard cosmological model, dark energy is a late bloomer. For the first 9 billion years of cosmic history, it was a negligible component of the universe's energy budget. Its effects only became apparent recently as matter thinned out. But what if it wasn't completely dormant in the early days? What if there was a form of early dark energy that played a role shortly after the Big Bang? This is a relatively new idea motivated by a growing and perplexing tension in cosmological measurements. We have two primary ways of measuring the current expansion rate of the universe, a value known as the Hubble constant HO. The first method involves looking at the local universe. We measure the distances to relatively nearby objects like Cepheid variable stars and Type Ia supernovae, and measure their recession velocities. This gives us a direct measurement of how fast the universe is expanding today. This method, pioneered by teams like the SHWS supernovae H0 for the equation of state of dark energy team led by Adam Riess, gives a value of about 73 kilometers per second per megaparsec. The second method involves looking at the early universe. We use the incredibly detailed map of the cosmic microwave background CMB from the Planck satellite. The CMB is the leftover heat from the Big Bang. By analyzing the patterns in this ancient light and feeding them into our standard lambda CDM model, we can predict what the expansion rate should be today. This method gives a value of about 67.4 kilometers per second per megaparsec. These two numbers do not agree. The discrepancy is about 9%, and the error bars on both measurements are small enough that it's very unlikely to be a statistical fluke. It's a genuine tension. It suggests that either there is some unknown error in one or both of the measurements, or our standard lambda CDM model is wrong. Early dark energy is one of the more promising theoretical solutions to this Hubble tension. The idea is that for a brief period in the early universe around the time of recombination, when the CMB was formed, about 380,000 years after the Big Bang, there was an additional component of dark energy. This early dark energy would have briefly accelerated the expansion before decaying away into other forms of radiation or matter. How does this help? The presence of this extra energy component would have changed the physical size of a key feature in the early universe called the sound horizon. The sound horizon is the maximum distance that a sound wave could have traveled through the primordial plasma before the universe became transparent. The size of this sound horizon is imprinted on the patterns we see in the CMB. The Planck team measures these patterns and uses the lambda CDM model to infer the size of the sound horizon, and from that, the Hubble constant. If early dark energy existed, it would have made the universe expand faster during that period, causing the sound horizon to be smaller than the standard model predicts. When the Planck team analyzes the CMB data, if they assume the standard model, they are unknowingly using the wrong ruler, the wrong sound horizon size to calibrate their measurement. If you correct for this by introducing early dark energy, you can make the early universe prediction of the Hubble constant match the late universe measurement. The tension disappears. This is a clever solution, but it requires introducing a new, finely tuned component to our cosmological model. This early dark energy would have to appear at just the right time, with just the right strength, and then disappear quickly. It feels a bit like adding an extra gear to a machine to fix a specific problem? Is it a genuine insight into the early cosmos or just an ad hoc patch? The next generation of CMB experiments, like the Simons Observatory and CMB-S4, will map the CMB with even greater precision. They will be able to test the early dark energy hypothesis by looking for specific signatures it would leave in the polarization of the CMB light. If those signatures are found, it would not only solve the Hubble tension, but also tell us that the story of dark energy is far more complex than we thought, with different forms of it playing roles at different cosmic epochs. Number 8, could we ever create it in a lab? Dark energy has an incredibly low energy density, but it's not zero. This raises a fascinating question: could we ever hope to produce and study it on Earth in a laboratory setting? The answer, for the most part, is a resounding no, and the reason comes down to a fundamental clash between the two pillars of modern physics: general relativity and quantum mechanics. Dark energy is a gravitational phenomenon. Its existence is inferred from its effect on the expansion of space-time, which is the domain of general relativity. Our laboratory experiments, on the other hand, are governed by the laws of quantum mechanics and the standard model of particle physics, which describes the forces and particles at a microscopic level. The problem is that gravity is astonishingly weak compared to the other forces. Consider the Casimir effect. First predicted in 1948 by Dutch physicist Hendrik Casimir, this is a real, measurable quantum phenomenon. If you place two uncharged parallel metal plates very close together in a vacuum, they will be pushed together by a tiny force. The reason is that the space between the plates can only sustain virtual particles of certain wavelengths, while the space outside can sustain all wavelengths. This creates a pressure difference, a tiny negative pressure between the plates that pushes them together. This is a form of vacuum energy, the same concept that is often invoked to explain dark energy. So, have we created dark energy in a lab? Not really. The Casimir effect produces an attractive force, not a repulsive one like dark energy. More importantly, while it's a real effect, it's a local one that depends on the boundary conditions of the plates. Dark energy, as we observe it, is a property of the vacuum itself, everywhere, with or without boundaries. The fundamental challenge is one of scale. To create a measurable gravitational effect, you need an enormous amount of mass or energy. Even the most powerful particle accelerators, like the Large Hadron Collider LHC, are dealing with energies that are minuscule on a gravitational scale. The energy densities created in particle collisions at the LHC are immense, far greater than the energy density of dark energy. But they exist in a microscopic volume for a fleeting instant. The gravitational effect of these collisions is completely negligible. To see the kind of space-time curvature that dark energy produces on a cosmic scale, you would need to sustain its energy density over a vast volume. That's simply beyond any conceivable technology. If dark energy is a new field, like quintessence, it might be associated with a new particle. This particle would have to be incredibly light, with a mass many, many orders of magnitude smaller than any known particle, and it would have to interact extremely weakly with ordinary matter. Otherwise, we would have detected it already in our experiments. Searching for such a particle is like searching for a ghost. It's possible that experiments looking for other weakly interacting particles, like actions a dark matter candidate, might stumble upon it, but it's a long shot. The only conceivable way to interact with dark energy would be to somehow alter the properties of the vacuum itself on a large scale. This is the realm of pure science fiction. It would require manipulating the fundamental constants of nature or creating energy densities far beyond anything we can imagine. So, for the foreseeable future, our lab is the universe itself. We can't put dark energy in a test tube. We have to study it by observing the behavior of galaxies and the fading light from ancient supernovae. It is a substance whose properties are written on the largest possible canvas, and we are limited to reading them from a very great distance. The challenge is not in building a machine powerful enough to create it, but in building telescopes precise enough to decipher its subtle cosmic message. Number 7. Is it related to cosmic inflation? The very early universe, in the first tiny fraction of a second after the Big Bang, is thought to have undergone a period of hyperacceleration called cosmic inflation. In a mind-bogglingly short time, about 10 raised to the power of 32 seconds, the universe expanded by a factor of at least 10 raised to the power of 26. This inflationary epoch was driven by a hypothetical field called the inflaton field, which would have had properties remarkably similar to dark energy, a powerful negative pressure that drove exponential expansion. The inflation theory is very successful. It explains why the universe is so large, so smooth, and so flat. After this brief, violent burst, the inflaton field is thought to have decayed, releasing its energy and creating the hot soup of particles that became the universe we know today. The expansion then continued, but at a much slower, decelerating rate, governed by the gravity of all that new matter and radiation. Then, billions of years later, acceleration started up again, driven by dark energy. This leads to a tantalizing question: are these two periods of cosmic acceleration related? Is dark energy some kind of leftover remnant of the inflaton field, or is the inflaton a form of primordial dark energy? On the surface, the two phenomena look very similar. Both involve a scalar field with negative pressure causing the universe to accelerate. However, the energy scales are vastly different. The energy density of the inflaton field during inflation would have been immense, perhaps 10 raised to the power of 100 times greater than the energy density of the dark energy we see today. If they are the same field, some mechanism would be needed to explain why its energy dropped so catastrophically after inflation and then stabilized at the tiny non-zero value we observe now. This is a major theoretical challenge. Many models of quintessence, the idea that dark energy is a dynamic field, are inspired by models of inflation. In some Hawking models, the field that drove inflation gets frozen in place after the Big Bang. For billions of years, it does nothing. Then, recently, it thaws and begins to slowly roll again, acting like dark energy. In tracking models, the dark energy field's density is designed to track the dominant energy density of the universe's first radiation, then matter before eventually taking over itself. These models attempt to create a unified picture of the universe's acceleration history, linking the beginning to the end. It feels elegant to think that the same fundamental physics could be responsible for both the initial burst that created our large universe and the gentle, persistent push that is now driving it apart. However, there is no direct evidence to link the two. They remain separate pillars of our cosmological model, invoked to explain observations at very different times in cosmic history. Inflation explains the state of the universe at 10 raised to the power of 32 seconds, while dark energy describes its behavior over the last 5 billion years. One way to test for a connection would be to look for its consequences. If the same field is responsible for both, its properties might be constrained by both early and late universe observations. For example, the quantum fluctuations of the inflaton field during inflation are believed to be the seeds of the large-scale structures we see today. The precise nature of these fluctuations, which we can measure in the cosmic microwave background, depends on the properties of the inflaton. If we can also measure the properties of dark energy with high precision, for example, by determining if its equation of state, W, is different from 1, we can see if the two are consistent with being caused by the same underlying field. For now, the connection is purely speculative. It's a beautiful idea that could potentially unify two of the biggest mysteries in cosmology. But it's also possible that it's a complete coincidence. The universe might have just used the same trick twice, with two completely unrelated fields to make itself accelerate. Number 6. Could it be a sign of extra dimensions? Our everyday experience is of a universe with 3 dimensions of space and 1 of time. But for over a century, physicists have entertained the idea that there might be more dimensions than the ones we see. In the 1920s, Theodore Kaluza and Oskar Klein proposed that a fifth dimension could unify gravity and electromagnetism. Modern string theory, candidate for a theory of everything, requires at least 10 dimensions to be mathematically consistent. Usually, these extra dimensions are thought to be curled up or compactified to a microscopic size so small that we can't detect them. But what if they are not? What if they have a real large-scale effect on our universe? Some physicists have proposed that the mystery of dark energy could be a sign that we are interacting with these hidden dimensions. One of the most prominent of these ideas is known as brain-world cosmology. The name comes from the idea that our four-dimensional universe is a brane, short for membrane, embedded in a higher dimensional space, often called the bulk. In this picture, all the particles and forces of the standard model electrons, quarks, light are confined to our brain. We are stuck on it, we can't leave, but gravity is different. In some of these models, gravity is a property of the full higher dimensional spacetime. It can travel through the bulk, off our brain. This could explain why gravity is so much weaker than the other fundamental forces. Most of its strength could be leaking out into the extra dimensions. It also offers a radical alternative to dark energy. In the DGP Diwali-Gabadadze-Parati model, mentioned earlier in the context of modified gravity, this leakage of gravity becomes more significant over very large distances. On the scale of the solar system, gravity behaves just as Einstein predicted. But on the scale of billions of light years, the leakage makes gravity appear weaker. This weakening of gravity's pull over cosmic distances would cause the expansion of the universe to accelerate. You don't need a mysterious repulsive energy, you just need a gravity that gets tired and leaks away. Another possibility is that the extra dimensions themselves have an effect on our brain. The Casimir energy that arises from quantum fluctuations in the vacuum depends on the geometry of space. If there are extra dimensions, their size and shape could contribute to the vacuum energy of our universe. It's possible that the interactions between our brain and other brains, or the geometry of the bulk itself, could create a small positive cosmological constant on our brain, driving the acceleration we observe. These are highly speculative and mathematically complex ideas. They are at the very frontier of theoretical physics. One of the major challenges is that they often predict other, more testable phenomena. For example, some brain world models predict that gravity should deviate from the inverse square law at very small distances, sub-millimeter scales. Despite very sensitive experiments, no such deviation has ever been found. They can also predict subtle violations of fundamental principles like the equivalence principle, which states that gravity affects all objects equally. These violations have also not been observed. Despite the lack of evidence, the idea remains compelling because it tackles the dark energy problem from a completely different direction. It suggests that the answer isn't a new particle or a new field within our universe, but a new understanding of the nature of space-time itself. It hints that the cosmos might be far larger and more complex than we can perceive, and that the accelerating expansion is a shadow of a higher dimensional reality. Number 5, will dark energy destroy the universe? The discovery of dark energy didn't just change our understanding of the universe's past, it completely rewrote the script for its future. The ultimate fate of the cosmos is now tied directly to the nature of this mysterious force. And depending on what it is, the end could be slow and cold or spectacularly violent. The future scenarios are primarily determined by the equation of state parameter, W, which is the ratio of dark energy's pressure to its energy density. The first and most favored scenario is based on dark energy being a cosmological constant, where W equals 1 exactly. This leads to a future known as the Big Freeze, or heat death. In this case, the density of dark energy remains constant. As the universe continues to expand, galaxies will be pushed farther and farther apart. The acceleration will become exponential. Any galaxy that is not already gravitationally bound to our own Milky Way in what's called the local group will eventually recede from us faster than the speed of light. This doesn't violate relativity because it's space itself that's expanding. The light from those galaxies will be stretched so much that it will never reach us. They will cross our cosmic event horizon and disappear from our view forever. The sky, as seen from our distant descendants, will become an increasingly lonely place. One by one, the familiar galaxies will vanish. After about 100 billion years, virtually every galaxy outside our own local group will be gone from sight. The universe beyond our small island of galaxies will be dark and inaccessible. The story then becomes one of slow decay. The remaining stars in our merged supergalaxy, Milkometa, will eventually burn out. The universe will be filled with dead stars, black holes, and cooling embers, over immense, unimaginable timescales, trillions upon trillions of years. Even these will decay through processes like proton decay and Hawking radiation from black holes. The universe will approach a state of maximum entropy, a cold, dark, empty void, with only a diffuse bath of low-energy particles. It's a quiet, desolate end. The second possibility is that dark energy is a form of quintessence, with W slightly greater than -1 e.g. W equals 0.9. In this case, the dark energy field is slowly losing energy. Its density would decrease over time, albeit very slowly. The cosmic acceleration would weaken. The future might still be an eternal expansion and a big freeze, but it would be a less dramatic one. In some specific models, it's even possible for the dark energy field to eventually become attractive, causing the acceleration to halt and the universe to recollapse in a big crunch, a fiery reversal of the Big Bang. This is considered unlikely given current data. The third and most terrifying possibility is phantom energy, where W is less than 1 e.g. W equals 1.1. In this scenario, the density of dark energy increases as the universe expands. The repulsive force gets stronger and stronger over time. This leads to the Big Rip. The runaway acceleration would eventually become so powerful that it would overwhelm all other forces. The process would start on the largest scales and work its way down. About 60 million years before the end, the repulsive force would be strong enough to unbind the Milky Way, sending its stars flying into the void. A few months before the end, it would tear apart the solar system. In the final minutes, the Earth would explode, and in the last 10 raised to the power of 19 seconds, the phantom energy would become strong enough to overcome the strong nuclear force, and it would rip apart individual atoms. The end would be a final singular moment where the fabric of space-time itself is torn asunder. Our current observations suggest that W is very close to 1, making the Big Freeze the most likely outcome. But the error bars still include the possibility of a Big Rip. The fate of everything hinges on the precise value of a single number that we are still struggling to measure. The difference between Wu equals 0.99 and Wu equals 1.01 is the difference between a quiet fade to black and a universe torn to shreds. Number 4, does it have anything to do with the Higgs boson? The Higgs boson, discovered at the LHC in 2012, was the final missing piece of the standard model of particle physics. It is an excitation of the Higgs field, an energy field that permeates all of space. The interaction of other particles with this field is what gives them their mass. Without the Higgs field, the universe would be a very different place, with no atoms, no stars, and no planets. The Higgs field, like dark energy, is a scalar field that fills the entire universe and has a non-zero energy value in the vacuum. This has led to an obvious and tantalizing question: could the two be related? Could the Higgs field itself be the source of dark energy? On the face of it, it seems like a neat idea. We know the Higgs field exists. It has a vacuum expectation value, which means the ground state of the field is not zero. This vacuum energy should, according to general relativity, contribute to the energy density of the universe, and act like a cosmological constant. You know, it feels like a natural candidate, one that doesn't require inventing a completely new, unknown field. But when you do the calculation, you run into a catastrophic problem. The energy of the Higgs vacuum, as predicted by the Standard Model, is enormous. It's about 10 raised to the power of 56 times greater than the observed energy density of dark energy. This isn't the 10 raised to the power of 120 mismatch that comes from more general quantum field theory calculations, but it's still a colossal failure. It predicts a universe that would have expanded so violently and so quickly that no structures could have ever formed. So the simple answer is no. The Higgs field, as we currently understand it, cannot be the source of dark energy. Its contribution to the vacuum energy is far too large. This leads to a deeper puzzle. If the Higgs field contributes this huge amount of energy to the vacuum, and other quantum fields contribute even more, then there must be some other unknown physical process or symmetry that cancels out almost all of this energy with exquisite precision, leaving behind just the tiny, tiny amount we observe as dark energy. We have no idea what this cancellation mechanism could be. However, that doesn't mean the two are completely unrelated. Some more speculative theories propose a direct coupling between the Higgs field and a quintessence field. In these Higgs portal models, the Higgs acts as a mediator or portal between the known particles of the Standard Model and the hidden physics of the dark sector. This could lead to interesting cosmological consequences, potentially affecting the evolution of the universe in the very early moments after the Big Bang. Another fascinating connection comes from the stability of the Higgs vacuum itself. The precise masses of the Higgs boson, about 125 GeV, and the top quark, about 173 GeV, are crucial parameters. When physicists use these measured values to calculate the stability of the Higgs potential, they find that our universe appears to be in a metastable state. This means the vacuum we live in might not be the true lowest energy vacuum. It could be a false vacuum, a temporary state that is stable for now, but could, in theory, tunnel into the true vacuum state. This leads to the idea of a big slurp or vacuum decay, where a bubble of true vacuum could spontaneously appear and expand at the speed of light, destroying everything in its path. This doesn't directly explain dark energy, but it shows how the physics of the Higgs and the vacuum are intimately linked to the ultimate fate and nature of our cosmos. The very field that gives mass to particles might also hold the key to understanding the stability of space-time itself. While the Higgs is not the simple answer to the dark energy puzzle, it's clear that a final understanding of the vacuum will require a deep synthesis of both particle physics and cosmology. Number 3, how can we be sure it's not all a big mistake? The evidence for dark energy is compelling. It comes from multiple independent lines of observation. The original discovery came from Type Ia supernovae, showing that the expansion is accelerating. And further evidence comes from the cosmic microwave background. The detailed patterns of temperature fluctuations in the CMB, as measured by the Planck satellite, are a snapshot of the early universe. When we feed this snapshot into our cosmological models, they only match the universe we see today if about 68% of the cosmic energy budget is dark energy. A third line of evidence comes from baryon acoustic oscillations, BAO. These are relic sound waves from the early universe that left a subtle imprint on the distribution of galaxies. They act as a standard ruler to measure cosmic distances. BAO measurements also confirm an accelerating expansion. The agreement between these different methods, supernovae, a standard candle, CMB early universe physics, and BAO, a standard ruler, is what gives cosmologists confidence that dark energy is real. It's not just one experiment with a potential flaw. It's a consistent picture painted by different techniques looking at different eras of cosmic history. But science is about skepticism. How could we be wrong? The most straightforward error would be in the data itself. For the supernovae, the assumption is that Type Ia explosions are truly standard candles. What if they are not? What if distant supernovae, which exploded billions of years ago in a younger, chemically different universe, were intrinsically dimmer than nearby ones? This could make them look farther away than they really are, creating the illusion of acceleration. Astronomers have worked tirelessly to account for these potential evolutionary effects and have found no evidence that they can explain the data, but it remains a source of systematic uncertainty. Another possibility is a mistake in our interpretation. As discussed before, our conclusion relies on the assumption that the universe is, on average, homogeneous. If our local region of the universe is not representative of the whole, for example, if we are in a large cosmic void, it could skew our measurements. Again, current observations of the CMB and large-scale structure do not support this, but it cannot be ruled out with 100% certainty. Then there is the possibility of a flaw in our fundamental theory, general relativity. This is the modified gravity argument. Perhaps there is no dark energy, and gravity is simply weaker on large scales. While general relativity has passed every test with flying colors so far, these tests have been primarily in strong gravity regimes like near black holes or in our local solar system. The cosmic acceleration is a phenomenon of weak gravity over immense distances, a regime that is not as well tested. Scientists are actively trying to break the dark energy paradigm. The Vera C. Rubin Observatory in Chile will conduct the Legacy Survey of Space and Time Lust, a 10-year survey that will catalog billions of galaxies and thousands of supernovae. It will provide a dataset of unprecedented size and precision to test the standard model. The Euclid and Nancy Grace Roman space telescopes will map the dark universe in 3 dimensions, testing the growth of structure and the geometry of space to see if it matches the predictions of dark energy or points towards a modification of gravity. The existence of dark energy is a radical claim. It requires us to accept that 95% of the universe is made of substances we cannot see and do not understand. Such a claim demands extraordinary evidence. While the current evidence is strong, the history of science is filled with examples of accepted theories being overturned by new data or a new perspective. The possibility, however remote, that we have made a fundamental error in our measurements or our model is a thought that haunts every cosmologist. It is the necessary skepticism that drives the search for more and better data. Number 2, the worst prediction in the history of physics. There is a dark cloud hanging over the idea that dark energy is the cosmological constant, the energy of the vacuum. It is not a small problem or a minor discrepancy. It is the single largest disagreement between theory and observation in the entire history of science. It is often called the cosmological constant problem, or more bluntly, the vacuum catastrophe. The problem arises when you try to calculate the value of the cosmological constant from first principles, using our best theory of the subatomic world quantum field theory. According to quantum mechanics, empty space is not empty. It is a roiling sea of virtual particles that constantly pop in and out of existence. These fleeting particles have energy. The sum of all this energy is the vacuum energy, and it should behave exactly like a cosmological constant. Physicists can try to estimate how large this vacuum energy should be. They sum up the contributions of the quantum fluctuations of all the known elementary particles. The result is a number that is staggeringly, absurdly large. The theoretical prediction for the vacuum energy density is about 10 raised to the power of 120 times larger than the value we observe from cosmic acceleration. Let's try to put that number 10 raised to the power of 120 into perspective. It is a 1 followed by 120 zeros. There are estimated to be about 10 raised to the power of 80 atoms in the entire observable universe. If you were to measure the size of the observable universe and your prediction was off by 10 raised to the power of 120, it would be like predicting its diameter to be larger than the actual universe by a factor of 10 raised to the power of 40. It is a level of wrongness that has no parallel in science. This is a deep, fundamental crisis. It tells us that our two great theories of the universe, general relativity, which describes gravity, and the large-scale cosmos and quantum field theory, which describes the small-scale particle world, are in profound disagreement. Something about the way we are combining them is catastrophically wrong. Physicists have tried for decades to solve this problem. One early hope was that some unknown symmetry in nature would make the vacuum energy exactly zero. For example, a theory called supersymmetry proposes a partner particle for every known particle. The contributions of these partner particles to the vacuum energy would be negative, and if the symmetry were perfect, they would exactly cancel the contributions from the normal particles, resulting in a vacuum energy of zero. This would have been a beautiful solution. The problem is that we haven't found any of these supersymmetric particles, and even if they exist, we know the symmetry must be broken at low energies, otherwise we would have seen them, which ruins the perfect cancellation. So if the total is not zero, why is it so close to zero? The observed value of dark energy is not zero, but it is 120 orders of magnitude smaller than the natural value predicted by theory. Or it's as if you had two piles of sand, each weighing 1 trillion tons, and you wanted to balance them on a scale so perfectly that they were within a single grain of sand of each other. It requires an unbelievable amount of fine-tuning. Some unknown physical principle must be canceling out the enormous contributions from the quantum vacuum, leaving behind just a tiny little residue that we call dark energy. This is arguably the biggest open question in fundamental physics. It's not just a problem for cosmologists, it's a problem for anyone trying to build a unified theory of nature. The existence of dark energy is not the puzzle. The puzzle is its ridiculously small value. It suggests a profound flaw in our understanding of the vacuum, gravity, and the very nature of energy itself. Until we can explain why the vacuum energy is not gigantic, we cannot claim to truly understand dark energy or the universe it dominates. Number 1, are we fundamentally misunderstanding everything? This is the ultimate haunting question, the one that contains all the others. The discovery of dark energy wasn't just another piece in the cosmic puzzle. It was a piece from a completely different puzzle box that somehow ended up on our table. It doesn't fit with anything we know. It challenges our most basic assumptions about the universe. For centuries, our understanding of the cosmos was built on the idea that gravity is the dominant force on large scales. While it pulls things together, the story of the universe was a story of structure formation, of matter clumping together to form stars, galaxies, and clusters. As dark energy turns this story on its head. It tells us that the ultimate driver of the cosmic narrative is a repulsive force we don't understand, made of a substance we can't identify that is pushing everything apart. The cosmological constant problem, the 120 order of magnitude discrepancy, is not just a numerical error. It's a sign that our fundamental picture of reality is broken. It suggests that our understanding of the relationship between matter, energy, and space-time, the very foundation of physics, is deeply flawed. It's possible that the concepts of vacuum and energy, as we currently define them, are naive approximations of a much deeper and stranger reality. The coincidence problem, why now, hints at a possible flaw in our understanding of time and our place in it. Does the anthropic principle mean that the laws of physics are not universal, but are instead just the particular set of laws that exist in our cosmic neighborhood, a neighborhood selected for its ability to produce life? This would be a demotion of our scientific aspirations, a retreat from the search for universal truths to a more provincial understanding of our own cosmic bubble. The alternatives to dark energy are just as radical. The idea of modified gravity means that one of the most successful and elegant theories in all of science, general relativity, is wrong. The idea of extra dimensions suggests that the world we perceive is just a slice of a much larger, higher dimensional reality. Every path forward seems to lead to a revolution. To solve the mystery of dark energy, we can't just make a small adjustment to our models. We likely need a new paradigm, a new way of thinking about the fundamental components of the universe. This might require a successful theory of quantum gravity, one that finally unifies Einstein's theory of the large with the quantum theory of the small. It might require the discovery of new particles or new forces that completely rewrite the standard model. This is what keeps physicists up at night. It's not just the technical details of the data or the complexity of the equations. It's the sense that we might be on the verge of a breakthrough as profound as the ones initiated by Newton or Einstein. But it's also the fear that we might be fundamentally stuck, that the answer to the dark energy puzzle lies in a realm of physics so far beyond our current experimental reach that we may never grasp it. Dark energy is a statement of our ignorance. It is a label we have placed on the edge of our map of the universe. It represents the 95% of reality that remains dark to us. The haunting questions it raises are not just about the cosmos, they are about the limits of our own knowledge. They force us to confront the possibility that, despite all our progress, we have only just begun to understand the true nature of the universe we live in.